Today we want to discuss a new method of adjusting the trigger circuits of a Tektronix 535-545 series oscilloscope. We're interested in making trigger circuit adjustments because they affect the operation of three controls on the front panel of the scope. First of all, the triggering level control here, the trigger slope selector switch here, and the mode selector switch here. In any modern general-purpose oscilloscope, amplitude level selection of triggering information is a necessity. In other words, we want to be able to select a level at which the information fed into the trigger circuit will cause the sweep to generate a trace across the cathode ray tube. And the instant where a trace will be generated will be that instant of time when the trigger information crosses a selected level amplitude. We also would like to have facilities so that we have slope selection. In other words, this is a positive slope, this is a negative slope, this is a positive slope, and this is a negative slope. But note carefully that the ground line, 0 volts DC, runs through the middle of this sketch, and that this DC voltage is actually positive in reference to ground, whereas this DC voltage is negative in reference to ground. So in a good trigger system, we will have independent controls for slope and for amplitude. We can choose a level here, 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 or we can choose a level below ground, in other words, a negative DC voltage where we want triggering to take place, such as on this waveform. We will also be able to choose by setting the slope selector switch to a positive slope. We can choose to trigger at this instant of time, or we can choose to trigger at this instant of time, or we can choose to trigger at this instant of time. Next, before we give an actual demonstration of how the adjustments are made, let's briefly run through a discussion of the various controls and how these controls affect the circuits in which the control is located. First of all, how do we get amplitude level selection? Well, in a 535-545 oscilloscope trigger system, we use a bistable multivibrator consisting of two triodes. It's labeled V20 in your schematics. A bistable multivibrator is characterized by having two stable states, one in which the left-hand tube is conducting and the right-hand tube is cut off, and the other stable state where the left-hand tube is cut off and the right-hand tube is conducting. Now, for the purposes of our preliminary discussion, let's assume that the left-hand tube is conducting and that the grid is elevated, say right up here on the input waveform. This is just a sine wave that we've drawn to show a possible trigger fed into the shaper circuit, the trigger shaper circuit. As the grid is lowered in the left-hand tube and we begin to approach a certain critical level, which we shall call the trip level for this particular multivibrator, current in the left-hand tube begins to decrease, the plate begins to rise, and through a voltage divider lifts the right-hand grid of the right-hand tube. Eventually, the right tube will begin to conduct a little bit of current, and at that time the multivibrator snaps over, and the feedback path goes from this grid to that plate, around through the divider network to this grid, through the cathode circuit, and back to the original grid from which we started. This is a positive feedback loop, therefore the circuit is a multivibrator, and we will have a snap action taking place in which current which has been flowing in this tube now ceases to flow, and current begins to flow in the right-hand tube. Now, it turns out in analyzing the whole sweep generator circuit of a 530-540 series scope that we are interested in when the right-hand plate makes its negative excursion, in other words, goes negative, at time t sub 1. And so when current flows in the right-hand tube, the plate will pull down. Therefore, the instant of time that we want to know about will be that instant of time when the left-hand grid goes down through the critical trip level for the multivibrator. Having snapped over, the multivibrator then sits with current in the right-hand tube flowing, no current in the left-hand tube, until the input grid goes through the rest of the waveform and begins to approach another critical voltage level, which we have labeled reset. The reset voltage level will be something like 1 4/10 volts more positive for this multivibrator than is the voltage level of the trip point. As the input grid is lifted and begins and approaches the reset level and finally penetrates the reset level, the multivibrator will snap back over to the original condition, which is current flowing in the left-hand half and no current flowing in the right-hand half. Now we're pretty interested in determining, for long service of the trigger shaper circuit, we're interested in finding out what the amplitude of the hysteresis gap, and the hysteresis gap is defined as being the difference in voltage level between the 200-volt trip level and the reset level. We're interested in making that hysteresis gap as wide as possible and still make the instrument perform within catalog specifications, which says that a 200 millivolt square wave applied to the external trigger input of the scope shall make this trigger shaper circuit snap back and forth through its cycle of operations. Now the width of the hysteresis gap in a bistable multivibrator is controlled basically by the loop gain of the feedback circuit. In other words, the gain from this grid to that plate, around through this grid to that cathode, back through the common cathode circuit to the grid. And that gain can be determined in two ways, or be set in two ways. First, by adjustment of the trigger sensitivity pot, which is one of the controls we're going to show you how to set. And secondly, by changing the size of the plate load resistor in the left-hand plate. Changes of the trigger sensitivity pot will either widen or narrow the hysteresis gap. And we're interested in finding out just how wide that gap is for a particular instrument. Next, it is necessary to adjust the whole trip and reset voltage waveform for the multivibrator up and down. We have to be able to adjust this total gap up and down in reference to a driving signal, which we will show you on another card, which is applied to the input grid. By changing the triggering level centering potentiometer, we actually move the trip level up and down as far as DC volts are concerned and set the trip level at some specific DC voltage as required by the instrument on which you are working. Now, because the hysteresis gap is determined by the trigger sensitivity pot and the loop gain of the multivibrator, this gap will maintain a certain width depending upon how you have adjusted the trigger sensitivity pot, and therefore both the trip level and the reset level will be lifted up or down by turning the triggering level centering pot. So the second adjustment that we'll be interested in making as far as the trigger shaper stage is to set the triggering level centering. Now let's add the trigger amplifier circuit to the basic trigger shaper circuit previously discussed. Since we want trigger information to be fed into the trigger circuit and cause the generation of a sawtooth or a trace across the cathode ray tube, and we want trigger information to be handled at or about ground level, about 0 volts. In other words, we want to be able to trigger from a signal which is above ground or below ground by a specified number of volts. In other words, we want amplitude selection availability. We therefore use a cathode coupled amplifier stage arranged as a comparator circuit. We are able to feed trigger information in externally the way we have our switch thrown at the moment. We will feed information in externally to the left-hand grid of the cathode couple amplifier. If you remember your cathode couple amplifiers, the output plate goes in the same direction as the input grid. If we lower the input grid with a piece of trigger information, the output plate will be lowered. Now, over in the trigger shaper, we showed that we're interested in knowing about the instant of time, or we want triggering to take place at the instant of time marked T sub 1. In other words, when the output plate of the trigger shaper circuit goes negative. And that will occur when the input grid of the trigger shaper circuit moves negative through the trip level. And so the plate of the right-hand half of V8, the trigger amplifier, will have to be moving in the negative direction at the instant of time that we want a sweep developed, T sub 1. And so the input grid of the basic circuit, as shown on our card, will have to be moving in the negative direction. And at some critical level, which has been chosen by the triggering level control, the plate of V8, the right-hand section, will pull the grid of the trigger shaper down through the selected trip level, which has been established by the triggering level centering control. And at that instant in time, we will get a sweep across the cathode ray tube. I'm sure that it's apparent to you that in order to have a positive slope applied to the grid of the comparator tube and cause a negative going plate, that we will have to interchange the two grids. In other words, we will apply a positive going trigger to the right-hand grid, and because of the inversion that takes place in a triode tube, the plate will be moving down when the grid moves up. Therefore, for slope selection in a 540, 530 series oscilloscope, we just interchange the two grids with a switch, which has not been shown on this basic schematic. For discussion purposes, let's assume then that we're going to use a negative slope, someplace on a negative slope which we can show. Someplace we will choose a level. And at that instant of time, T sub 1, we want the trigger shaper circuit to snap over and produce a negative going pip, or a pulse which triggers off the sweep generator and produces a trace on the CRT. Now, these cathode coupled amplifiers make a fairly convenient voltage comparator. In other words, if we set a DC voltage using the front panel triggering level control and set a DC voltage on the right-hand grid, let's assume that we set that voltage to be plus 10 volts DC. Then and if the input grid, starting way positive, goes down through and just equals, and at the time it just equals plus 10 volts DC, the output plate will just have gone down through the 200 volt trip level of the Schmidt bistable multivibrator. So we can mark our diagram on the blackboard as plus 10 volts. And now, by choosing either a positive or a negative voltage to which we set the right-hand grid, in other words, by turning the triggering level control on the front panel, we can choose to set the right-hand grid at either a positive voltage or a negative voltage. And the limits of voltages will be determined by the particular Tektronix oscilloscope with which you are working. I might stop here and point out that the general processes, or the general adjustments, or the general idea of the adjustments that we're discussing today can be applied to many of our modern oscilloscopes. So just because we have mentioned a 530, 540 series oscilloscope does not mean that you cannot use the same system on a 515, a 551, and the rest of our modern scopes. Feeding external trigger information into the trigger amplifier, we have seen that we can choose the level where triggering will take place, and that the choice will be determined by where the level choice will be determined by where you will have set the triggering level control and established a DC voltage for the right-hand grid. Now, when we move the switch right here to internal trigger information, remember that internal trigger information is picked out of the vertical amplifier at a fairly high DC voltage. In other words, the trigger information is superimposed. You could have, for instance, a waveform up here, a triggering waveform, and it would be superimposed on about plus 310 volts DC, measured from here to the 0-volt line. Now, somehow we must get rid of the DC component of the incoming trigger information from the vertical amplifier. And that's accomplished by the use of a voltage divider and by picking up a negative DC voltage from a regulated source, picking off a certain amount of that voltage and using it to buck out the positive DC voltage present up here. At the junction between these two resistors, we will therefore find a DC voltage which is proportional to the incoming trigger information and also to the setting of internal DC level adjust pot. So another adjustment we have to make in setting up the trigger circuits of a 535, 545, or rather the 530-40 series oscilloscope is to adjust the internal DC level so that when the trace on the cathode ray tube is centered, in other words, when we draw a horizontal center line or look at the horizontal center line on the graticule and place the trace, the dot corresponding to the vertical position of the trace, right on that horizontal center line, that we will have exactly 0 DC volts at the junction of the voltage divider here, and therefore fed on into the trigger amplifier tube. I should probably point out to you right now that the voltmeter is not part of the original circuit and it does not come with the oscilloscope. We have drawn a voltmeter between the two plates of the tube because that is the first step, or among the first steps, in setting up the trigger amplifier system. So suppose we go through now the sequence, in other words, the order in which these adjustments will be made. And a little later on I will go through an actual demonstration of the adjustments on a scope. Now, the first step is to find out what DC voltage must be applied to the right-hand grid of the comparator tube, which makes the plate of the tube, the right-hand section over here, this right-hand plate, which makes that plate stand perfectly still when you interchange the two grids. Remember that interchanging the grids change the slope from which we would trigger. In other words, from this slope to this slope, to move from this slope to this slope, we would have to interchange the two grids. And when we interchange the two grids, we certainly do not want the sweep to be triggered just by moving the slope selector switch from positive to negative slope. In other words, the process of changing these two grids should not make the right-hand plate move up or down. Now, several different methods could be figured out to find out when that plate stood perfectly still in reference to ground. In other words, when the voltage remained unchanged between that plate and ground as you interchange the two grids. But probably the simplest solution that has fairly recently been worked out is to use a voltmeter between the two plates. Since this amplifier stage functions as a differential amplifier, if this plate goes up, the left-hand plate will go down about the same amount, and you will see twice the voltage change on a voltmeter that you would observe if you connected a meter from this plate to ground. Another advantage of using a meter between the two plates is one of resolution. You can see a very tiny change between this plate and that plate, whereas it would be quite difficult to see a tiny change in the 200 volts DC, which will be the voltage at this plate in reference to ground. Now to discuss the order in which the adjustments are made, let's start first by moving back to external trigger. So we'll put our switch up here, and then external trigger information can be fed into either this grid or this grid depending upon our slope selector switch. By leaving the grid open right here, the grid is tied to ground with a 1 meg resistor approximately. Now by placing a voltmeter between the two plates of the tube, we will determine by moving the triggering level pot around near the 0 voltage position, we will find a DC voltage for the right-hand grid, which causes this plate to stand as many volts above or below this plate for the grids connected as shown here, as will occur when the grids are interchanged. In other words, by inverting the grids, switching them back and forth, this plate will stand the same number of DC volts above or below this plate in both conditions. That fixes the correct adjustment for the triggering level control pot. Now, with the meter still connected, the next step is to check for the possibility of gas or grid current caused by several different defects in a vacuum tube. We will check for grid current by taking a shorting strap from the external binding post and tying it to ground. In other words, we ground this grid. And we observe whether or not the plate of this tube moves in reference to the plate of this tube. The motion of one of these plates in reference to the others should probably not exceed 50 millivolts, and I will mention that again in our demonstration. Having checked this tube, both sections by the way, because grid current can flow in one section and not the other section of these twin triode tubes, by checking for grid current in both sections, we evaluate or find the quality of this tube. And if the tube is satisfactory, we proceed with the next adjustment, which will be the adjustment for internal trigger DC level. To make that adjustment, of course, we have to change the trigger selector switch to internal trigger information, and it will be necessary to center the cathode ray tube spot on the horizontal center line of the graticule. Then, by moving the internal DC trigger level adjust pot up or down, we can cause the DC voltage fed into the grid of the trigger amplifier tube to be exactly 0 volts DC. The next adjustment will be to go over to the trigger shaper stage. Since we have determined the DC voltage at which this tube wants to work, in other words, something about or around 200 volts positive in reference to ground, we next will have to make the trip level of the bistable multivibrator equal that 200 volt DC voltage obtained from this plate. You see there's a connection from this arrow right across to that grid. That adjustment is made by turning the triggering level centering pot until the multivibrator has just tripped. In other words, we're operating at that point. Next, we proceed to determine the correct setting for the trigger sensitivity pot itself. And that's done by measuring indirectly the hysteresis gap in volts. In other words, we want an adjustment here where this gap is set to something like 1 2/10 to 1 4/10 volts as shown here. Next, let's turn now and carry out a demonstration or make a demonstration on the scope itself. To start an actual adjustment on the oscilloscope, let's preset the front panel controls to the proper positions. First, turn up the intensity control until a visible spot can be seen on the cathode ray tube. Next, set the horizontal display switch on main sweep normal. Next, set the time per centimeter switch either on the 1 millisecond per centimeter position or the 100 microsecond per centimeter position. Set the trigger slope selector switch on external positive slope. Set the triggering mode switch on DC coupled in this position. Next, turn the triggering level control full clockwise and turn the stability control clockwise until the sweep just begins to free run. Find the spluttery condition and then turn the stability control counterclockwise about 10 or 15 degrees, and that's the last time you should touch the stability control. As the next step in our adjustment procedure, let's preset the trigger circuit adjustment pots to about mid-range. First, the triggering level centering pot should be set somewhere near the middle of its rotation. The slot will be vertical in this particular scope. Next, the trigger sensitivity pot should be set in about the middle of its range. The slot will also be vertical for this scope. Now, these presets probably would not have to be done on an oscilloscope in reasonably good working order. I've shown you these preset conditions with the thought that if somebody has turned these pots without understanding the correct adjustment of the trigger system, you may find them way off. And so a preset of these two controls will help you in the adjustment process. Next, let's put a clip lead between the junction of a pair of 470,000 ohm half-watt resistors to the end of a 56,000 ohm half-watt resistor. This ferrite bead is actually a parasitic suppressor in the middle of a clip lead, and you could use an ordinary straight piece of wire for the clip lead. When we connect the clip lead between the junction of the 470,000 ohm resistors and the 56,000 ohm resistor, we are really making it easy for you to adjust the triggering level control. And on the circuit schematic, the triggering level control has a range of about plus 100 volts to minus 100 volts at this point. And the two 470,000 ohm resistors mentioned in the previous steps, in other words, when we connected the jumper, are these two resistors, and therefore connecting the clip lead was really carried out by connecting this point to this point. Here's the 56K, and the result of making this connection across here is to reduce the DC voltage change at this point to about plus or minus 7 volts for a 530-540 series oscilloscope. Now connect the volt-ohm-meter leads to the 4.7K plate load resistors of the trigger amplifier tube. These resistors are the third and fourth resistor back on the ceramic strips, the inboard ceramic strips. So we make a connection to this resistor, and we make a connection to this resistor. Now, reviewing the position of the controls, the triggering mode switch is set for DC coupling. The trigger slope selector switch is set for plus external. The triggering level switch is anywhere at the moment. The stability control is set in the triggerable range of its rotation. Next, turn the meter to the 60-volt scale and adjust the triggering level control for 0 volts. Next, turn the trigger slope selector switch to negative external. And note that the meter reading is fairly low. So proceed to the 12 volts full scale range of the meter. Again, obtain a 0 by moving the trigger slope selector switch to plus external and turning the triggering level control until the meter reads 0 volts differential voltage between the plates of the trigger amplifier tube. Now turning the trigger slope selector switch to minus external, we read approximately 2 volts on the meter. Next, turn the triggering level control until the meter reads just half the voltage we have found. In other words, reads about 1 volt. Now turning the trigger slope switch back and forth between plus and minus internal, make a careful readjustment of the triggering level control so that the meter pointer does not shift its reading as you interchange the two grids of the trigger amplifier tube, which is accomplished by turning the slope switch from plus to minus. In other words, we make the right-hand plate of the trigger amplifier tube stand perfectly still in reference to the left-hand plate. The right-hand plate of that tube is running either 1 volt above or 1 volt below the left-hand plate. That voltage we read from the meter. Now take a 47 ohm half-watt resistor and clamp one end of the resistor in the ground binding post of the scope. Use the other end of the 47 ohm resistor as a grounding strap for the trigger input connector. With the trigger slope selector switch set to the plus external position, momentarily short the trigger input connector to ground and note the variation or the change in the meter reading. The meter should show less than a 50 millivolt change, which is one small division on the 12 volt range of this meter. A change in the meter reading shows the presence of grid current. Now, lest you become confused, let me point out that sometimes we carelessly say gas current, and it happens that gas current would be equally dispersed or equally distributed between the two halves of a twin triode tube. But it is possible for grid current to exist in one half of the tube which does not exist in the other half. For that reason, we have to check both grids of the input trigger amplifier tube. Now, watching the meter, we saw that there was very little shift as far as this grid is concerned, certainly less than 1 scale division on the meter. So now, moving the trigger slope selector switch to interchange the two grids, we can then ground the other grid. And we see again that less than 1 scale division of the meter results. That is, a change of less than 1 scale division results through grounding the grid. So this tube is satisfactory as far as grid current is concerned, and we can then proceed with the rest of the adjustments. If you find that the meter changes on the 12 volt range more than 1 small division, it would be best to replace V8, that is the trigger amplifier tube, and let the new tube get thoroughly warmed up and repeat the adjustments to this point. Now verify again that changing the slope selector switch from plus to minus external slope still causes the meter to stand perfectly still at about 1 volt. That shows that we have adjusted the triggering level control correctly. Now notice whether or not the white dot on the triggering level control stands exactly opposite the engraved 0 on the front panel. This particular dial is quite close. However, if you do notice an error, loosen the set screw and turn the knob on the potentiometer shaft until you have found a location for the knob where the white dot stands opposite the 0 and the control is properly adjusted as shown here. Next, turn up the intensity control on the cathode ray tube until you see a visible spot. Then with the vertical position control, set the spot on the horizontal center line of the scope. Next, turn the trigger slope selector switch to minus internal. Again, be sure you stay in DC coupled mode. Now, adjust the internal trigger DC level pot with a screwdriver so that the meter reads the same voltage as you have obtained before, namely about 1 volt. Now, by changing the trigger slope selector switch between plus and minus internal, you should see no change in the meter reading. In fact, now, by changing the trigger slope selector switch from plus to minus internal, And from plus to minus external, the meter reading should remain exactly the same. Being very careful not to disturb the position of the triggering level knob, carefully remove the shorting link and the meter leads from the scope. Next, with the trigger slope selector switch set on plus external, use a screwdriver and turn the triggering level centering pot clockwise to cock the bistable multivibrator in the trigger circuit, and then very slowly counterclockwise until the sweep produces just one trace across. I doubt that you will be able to see the trace across produced by the sweep generator. And then turn the control clockwise to again cock the bistable multivibrator, and again come very slowly counterclockwise until the sweep has just triggered. In other words, has just produced a trace across. And as soon as you have found the point where the sweep has just produced one stroke, remove the screwdriver. The control is now properly adjusted. Having completed the adjustment of the triggering level centering potentiometer, the next step is to verify adjustments so far. Set the triggering mode selector switch on internal plus or internal minus, makes no difference. Be sure you're in DC mode, and carefully turn the vertical position control counterclockwise for negative internal. Slowly counterclockwise until the sweep snaps one trace across the cathode ray tube. Note carefully that that occurs right at the horizontal center line. Now move the spot down below the horizontal center line, turn the trigger slope selector switch to internal positive, and generate with the vertical position control a very slowly changing leading edge, a positive going slope. And as that spot approaches the horizontal center line, note that the trigger circuit causes the sweep generator to produce a trace right at the horizontal center line. If the position where the trace is generated occurs on the center line for both plus and minus positions of internal trigger slope, you have made a correct series of adjustments so far. Next, patch the calibrator across to the vertical amplifier. Set the gain of the vertical amplifier at about 200 millivolts per centimeter, and patch the calibrator also to the external trigger input. Set the trigger slope selector switch on plus or minus external, makes no difference. We'll leave it on plus external. Next, turn the calibrator on and adjust for the volts position, and set the output voltage at 200 millivolts peak to peak. Now, by carefully turning the triggering level control, you should be able to obtain a stable square wave on the face of the cathode ray tube, showing that the scope meets catalog specifications, which says that 200 millivolts fed in externally should produce a stable trace. Now comes the most important part of this new procedure. It is one additional step beyond any trigger circuit adjustment procedure that you have learned before. You may have your own method of adjusting the trigger system, and that method probably is satisfactory. If you like, you can use the new meter method just proposed, but add one important step, and that is to verify that the sweep will not trigger successfully on 100 millivolts peak-to-peak square wave fed in externally. We have just seen that it will trigger successfully on 200 millivolts peak-to-peak square wave fed in. So now let's change the calibrator square wave generator from volts to millivolts and the output control to 100 millivolts. We now have 100 millivolts peak-to-peak amplitude applied to the trigger system. Now, by a very careful adjustment of the triggering level control, note that a square wave, a steady display, cannot be obtained. And in that circumstance, the trigger system is correctly adjusted. In other words, the scope should not trigger successfully on 100 millivolts, but should and must trigger successfully on 200 millivolts input. If the trigger circuit does trigger successfully and you get a stable display with 100 millivolts square wave fed in, as I now show, turn the trigger sensitivity pot about 5 or 10 degrees counterclockwise, and again check to see, by a very careful adjustment of the triggering level control pot, that you cannot obtain a stable display of the 100 millivolt square wave fed in. Next step, go back and verify that 200 millivolts will produce a stable pattern on the cathode ray tube. You may have to readjust the triggering level control to get that stable pattern. Now, by verifying or by checking to see that 100 millivolts will not cause a stable pattern on the cathode ray tube, we have indirectly set the hysteresis gap of the bistable multivibrator, the trigger shaper stage, to be about 1 2/10 to 1 4/10 volts. And by setting a measurable hysteresis gap, we will be certain that aging of the tube will still leave the scope trigger system in a good usable condition. Now, for those of you having scopes with a preset stability control located in this corner of the scope, make the proper adjustment for the preset stability control according to the procedure outlined in your instruction manual. Now let's quickly summarize the steps that we've just gone through using our basic schematics. With the source selector switch set in the external position, in other words, no signal applied to the input grid of the trigger amplifier, we found a setting for the triggering level control pot so that this plate stood perfectly still in reference to this plate as we interchanged the two grids of the trigger amplifier tube. After finding that rotation for the triggering level control, or that position, we then shifted to internal source, internal triggers, and by centering the vertical amplifier spot, in other words, centering the cathode ray tube spot, which produces an equivalent 0 voltage from the vertical amplifier, we then adjusted the internal trigger DC level adjust pot so that 0 volts DC resulted at the junction of these two resistors. Now, having found that the plate of this tube wants to work at plus 200 volts DC, we then moved across into the trigger shaper stage and adjusted the triggering level centering pot until the bistable multivibrator had just tripped at 200 volts. Next, we applied a test signal, a 200 millivolt peak-to-peak square wave to the trigger input, again external, fed it through the triggering system to the grid of the bistable multivibrator, and then adjusted checked to see that the bistable multivibrator was driven through both halves of the cycle of operation. In other words, the square wave applied drove the input grid down through the trip level for this bistable multi and up through the reset level for every cycle of the square wave fed in. Next, we fed in 100 millivolts externally and through the gain of this amplifier stage and coming out of the plate and applied to the grid of the trigger shaper stage. We again checked to see that the bistable multi would not be successfully driven by a 100 millivolt square wave, which is too small an amplitude to drive the bistable multi through both the trip level and the reset level. In other words, the hysteresis gap has been set wide enough so that a 100 millivolt signal will not successfully operate the bistable multi. If we found that the 100 millivolt square wave did drive through both the reset and the trip level, in other words, did produce a continuous trace on the cathode ray tube, we then backed off on the adjustment, turned counterclockwise the trigger sensitivity pot until a 100 millivolt square wave will no longer cause a smooth trace to be developed or a continuous trace to be developed on the cathode ray tube. We sincerely hope that the method we have outlined today will help you in maintaining your Tektronix oscilloscope. 530, 540 scopes and a number of our other instruments can be adjusted using the same general method. The material that we've covered is a supplement and should be considered as a supplement to the printed material we have furnished you in instruction manuals. Good luck. Hope you're successful with your trigger circuit.